Hello and welcome to the introductory lesson for Chapter 2, Chemistry of Life. Now you may be wondering, why do we study chemistry when we're actually a biology class? However, it's the chemistry and the interaction of the atoms which create the molecules, which create the cells, which interact. And it's when you look at the interaction between atoms, it makes the understanding of the macromolecules such as proteins and carbohydrates and nucleic acids and lipids make more sense. And when you understand the concepts there and how those molecules interact, it gives you a better idea of how the body interacts. Okay, now, and we're not getting too technical. We're studying more about the biochemistry and a little bit about water. Okay, so let's look at a little introduction here. When we look at matter, just a little review here, all things are made up of matter. And you're made up of matter if you have mass and occupy space, so you matter. I know, cheesy joke. All matter is divided into pure substances and then impure substances. Pure substances are elements which are one type of atom. Example, oxygen, hydrogen. Compounds have two or more types of atoms that work together. So let's look at elements. Now you won't need to know all the elements of the periodic table, and there's over 200 of them, but there's really only about 60 in the body. However, really most things in the body are made by these 6 elements: oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. And I would like you to pay attention to these, so later on when we're talking about them and I say O, or it's actually O2, you understand that it is that it's oxygen. Don't worry about the percentages of the body. Don't worry about that. But I want you to realize that those are the 6 main elements. Then there are some lesser elements such as sulfur, potassium, sodium. Sodium and potassium are very important in nerve function. Chlorine, which usually reacts or travels with sodium, and it is the negative to the sodium's positive. Magnesium and iron is very important in blood. We'll talk about that when we talk about hemoglobin. Then there's some trace elements: chromium, cobalt, fluoride. Iodine's an interesting one. When we talk about iodine, that is used in, we'll talk about it when we get to the thyroid gland, because iodine is taken up by your thyroid gland. So if you see iodinized salt, that is to help your thyroid gland. Okay, good. So you don't need to memorize these, but I want you to get familiar with them so then later on when we talk about them, they make sense. Now, when you look at an atom is the smallest particle of matter. And an atom is composed of 3 subatomic particles: the protons and the neutrons, which are in the middle. When you change the number of protons, you change the atom. Then you have electrons that move outside and around the atom. It's the interaction of the electrons that will result in the bonding of compounds or molecules. Okay, so this is why we're talking a little bit about electrons. Good. Protons are positive, neutrons are neutral, electrons are negative. Okay, so 2 sodium molecules, we're walking down the street, one says, "Oh no, I've lost an electron," and the other one says, "Are you sure?" And he says, "Yeah, I'm positive." It's a little ion joke. Okay, when you lose electrons, you become charged. Okay, so when we talk about changing protons, when you change the number of protons, you change the element. When you change the number of neutrons, you get what's called an isotope. And when you have too many neutrons, you can get a radioactive isotope. So when we talk about radioactive uranium, you have a different isotope. And an isotope of cobalt is what is used in radiation therapy for cancer. Okay? Good. Now, when it comes to chemical bonds, there are two different ways that atoms interact with other atoms. They can do two things. They can either lose or gain their electrons, or they can share their electrons. And it has a lot to do with where the how many electrons I have in the outer energy level. Without getting into too much detail, electrons have shells that fill up. And when the shell fills up, it's usually filled with 8, with the exception of the inner shell. So 8 is kind of the happy number of energy. So when you look at it, here's a simple example. So here is a sodium atom, and it has 1 electron in its outer energy level. Here is a chlorine atom, and it has 7 in its outer energy level.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion.
Okay, just a little detail there. If it's positive charged, first off, an ion is a charged particle. If you're a positively charged particle, you're a cation. If you're a negatively charged particle, you're an anion. And when you put these charged particles into water, you get an electrolyte. So this is how come sodium and chlorine are electrolytes. Okay, so notice in an ionic bond, there's a loss or gain or transfer of an electron. So you end up with this completely positive charge and a completely negative charge.
Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
Okay, the reason I showed you this is that when elements share electrons with other elements, because they're both hanging on to the electrons, it is a stronger bond and it can't be broken up as easy. So this is why covalent bonds are a little harder to break apart. So this makes the molecule more stable than an ionic bond. And an ionic bond, you can put it in water and it will break apart. So I want you to pay attention to the bonds of covalent and ionic bonds. So ionic, you have a transfer, and covalent, you have a sharing. Now, when there's this transfer, when there's a transfer of electrons, it is stable until you put it in water. And then water, by its interaction, will interact with the charged particles. If you looked at water, because of the way the electrons interact, you've got, let me show you again with this diagram. So when you look at it, you have got...
Completed by sharing an electron with another hydrogen atom.
So the electrons are more around the oxygen. That makes this side, since electrons are negative, slightly negative. Not a true pulling, not a complete charge, but it's a slightly negative. And that makes the hydrogen end slightly positive. So because of that, it becomes what's called a polar covalent molecule. And it's polar because the electrons have sort of a slightly positive pole and a slightly negative pole. So when you look at that property of water, this slightly positive, they kind of look like the ears of Mickey Mouse. The slightly positives will break up the true negatives, and then the slightly negatives, which is the red oxygen end, will break up the positives. So this is how water, being a polar molecule, has the ability to break up ionic solids and dissociate them, making an electrolyte. So there's a lovely word here, an electrolyte right here. Okay. Another example of how the textbook will hide a vocabulary word. So electrolytes are particles that become charged in water. And an example here is calcium, sodium, chlorine are the main ones. Okay. And these are critical for muscle and heart function. Good. So that is an ionic bond. There is a loss or gain. Now, in a covalent bond, there is sharing. And because there is sharing, it holds on much tighter. And because they're both sharing the same electrons. You can have a single covalent bond where they share one, or an oxygen shares two pair with carbon dioxide, and that's when you get a double covalent bond. Double covalent bonds are a little more unstable than single covalent bonds because you have all this negativity in one area. Okay. Because of the way the bonds are, or the electrons are held, you can have, as I said, an uneven sharing of electrons, and that will result in what's called a hydrogen bond. Now realize that covalent bonds and ionic bonds are sharing inside the molecule, so they're intramolecular bonds. Hydrogen bonds are an extramolecular because it will have one hydrogen attracted to the slightly negative end of another molecule. So here's an example of the slightly positive end of the hydrogen attracted to the slightly negative end of the oxygen. And this results in an interaction that will hold but not really tight. So when you want things to pull apart, molecules to pull apart, such as DNA, you hold it together with hydrogen bonds. Or in the curling and the forming of the shape of proteins, you have hydrogen bond interactions. Okay, so I want to talk a little bit more about water and its interactions. So I'm going to end this video on bonding, and we'll start with another one of water to talk more about water. See you later.